watching HackTheFile. I'm Michael Lopez, and today we're going to be doing Chapter 9 in the Ethical Hacking book series, and this one is going to be Fuzzing for Zero-Day Vulnerabilities. Enjoy. Alright, here we go. Chapter 9 Fuzzing for Zero-Day Vulnerabilities. Asking the right questions takes as much skill as giving the right answers. Robert Half. Now, I just saw a video on zero-day vulnerabilities, and so this chapter is going to be very interesting to me. I hope to you too. Alright, what happens if an attacker scans a system and doesn't find any known vulnerabilities? Can they still gain access? Yes, but they'll need to discover a new unknown vulnerability. These unknown vulnerabilities are called zero-day vulnerabilities. And useful ones can sell for millions of dollars. Finding a zero-day vulnerability often begins with finding a software bug. Once a hacker discovers a bug, they can exploit it to their advantage. Attackers use bugs to steal data, crash programs, take control of systems, and install malware. Let's start by exploiting a famous bug that led to the Heartbleed vulnerability that crippled the internet. Then we'll explore 3 techniques used to discover bugs: fuzzing, symbolic execution, and dynamic symbolic execution. Case study: exploiting the Heartbleed OpenSSL vulnerability. The Heartbleed vulnerability takes advantage of a software bug in an OpenSSL extension called Heartbeat. This extension allows a client to check if a server is still online by sending a heartbeat request message. If the server is online, it replies with a heartbeat response message. After the server stores the heartbeat request message in its memory, it responds by reading its memory and returning the same message in the heartbeat response. It uses the stated length of the heartbeat message to decide how much of its memory it should read and send back. Here's the bug if a hacker sends a heartbeat. Here's the bug. If a hacker sends a heartbeat request message with a length longer than the actual request, the server will include additional parts of its memory in the response, some of which may contain sensitive information. What? Figure 9.1 illustrates this. So the heartbeat, user admin, password John, session idea, private key. So set 9 heartbeat, sent it back, sent to 31 heartbeat. They sent heartbeat, user admin, password John 31. How'd they do that? The hacker was able to read the contents of the server's memory, which include passwords and private keys. This type of attack is called a buffer overread, as we can read beyond the bounds of the designated memory buffer. Similarly, in a buffer overflow attack, a hacker uses a bug to write beyond the bounds of the designated buffer. Hackers often use buffer overflow attacks to upload reverse shells that allow them to control the machine remotely. This process is called remote code execution, RCE. Why can't we fix this bug by making all heartbeat messages a fixed length? Because heartbeat messages measure the maximum transmission unit, MTU, of the client's path to the server. The MTU is the maximum size of the packet sent along the path. A packet moves through the network. They pass through a collection of routers. Depending on its designation, on its design, each router handles packets up to a specific size. If a router receives a packet that is larger than the MTU, it breaks the packet into smaller packets, a process called fragmentation. These fragmented packets are then reassembled when they reach the server by probing the network with heartbeat request messages of different length. The client can discover the MTU along with its path and avoid fragmentation. Hold on. These fragmented packets are then reassembled when they reach the server by probing the network with heartbeat requests, messages of different lengths. Oh, okay, that makes sense. Creating an exploit. After you found a bug, the next question is how to exploit it. To your advantage, exploiting a bug in an intricate process as writing your own exploit requires detailed understanding of the system. The bug you've discovered is most likely specific to the particular software version, so the exploit you write must also be specific to that software version. If the software developers fix the bug, you're no longer able to exploit it. This is one of the reasons that state actors are so secretive about their capabilities. Knowledge of this bug will allow an adversary to fix it, after, after which the state actor's exploit will no longer work. The cycle continues. Old vulnerabilities are patched and new vulnerabilities are found. The Heartbleed bug predates the release of TLS 1.3, so TLS message exchange during the Heartbleed attack conforms to the TLS 1.2 protocol. Figure 9.2 shows the messages exchanged during the attack. So the client, hello, server certificate, server key exchange, server key done. Malicious heartbeat request, malicious heartbeat response. Messages exchanged between a client and a server during a heartbeat attack. The client initiates the connection by sending a client hello message. The server responds with several messages that end with a final server done message. As soon as we receive the server done message, we respond with a malicious heartbeat request, after which the server will send a collection of heartbeat responses containing the leaked information. Starting the program. Let's write a Python program that exploits the Heartbleed bug. The program will be longer than the program we normally write, so instead of showing a single block of the code, I'll break the program into sections and discuss each section individually. You can reconstruct the program by copying each section into a file called heartbleed.py. Before we begin coding, let's discuss the general overview of the exploit. We'll begin by establishing a socket connection to the server. Then we'll manually initiate a TLS connection by sending a client hello message. After we sent the hello message, we'll continue to receive packets until we receive the server done message. Once we receive this message, we'll transmit an empty heartbeat message with a stated length of 64 kilobytes. We choose kilobytes because it's the maximum possible length and will allow us to extract the most information. If the server is vulnerable, it will respond with 65 kilobytes of its memory. Because each heartbeat packet can hold only 16 kilobytes of data, the 64 kilobyte response will have to be split across 4 packets. By printing the contents of these packets, we can read parts of the server's memory. Let's begin by importing the libraries we'll use throughout this process. So you can pause it or you can follow along, but I'm gonna see if we have these installed on the Linux. So here we go. Let's open up a command. Oh, wait a minute. This one might be cool. This one we're actually gonna build Python program, or let's see if they've got it up here already. Because I am just gonna do it quick. Let me see. Not that one. All right, let's just see which one this is gonna be. So this one's gonna be. They want us to do it in pieces. I am not. Um, so this one is gonna be the what? Heartbleed.py. Yes. All right. So. Alright, we're gonna cheat, but I'm still gonna read this. I'm gonna go to HackTheFile, and we're gonna say create new folder. We're gonna call this Heartbleed. From here, we'll create new document. And we'll call this Heartbleed.py. Open this up. Paste that. We'll close it. Save it. There's Heartbleed.py right there. All written. So what we'll do is we'll look at this import. If you guys don't know how to use Python, I would suggest learning programming. Learn some Python. Take a Python class. I got a video that shows a Python class you can take. It's $100 and it's awesome. But here you go. It's already written for us. Okay. This is what I always do. Start that up. Okay, now read. Alright. Here's the imports. We'll use the command line arguments to pass options to our program. So we'll need the assist library to read these arguments. Then we'll use the socket and select libraries, socket, select, to establish a TCP socket connection, to the vulnerable server. Socket, select. Lastly, we'll use the struct and arrays libraries, struct arrays, to extract a package to extract and package the bytes associated with each field in the packets we receive. Writing the client hello message. Next, we'll construct the client hello message, which is the first message sent by the TLS protocol. The IETF outlines the TLS specification in the RFC R246. We'll use this specification to construct the packets that we'll send in this chapter. Figure 93 represents the layout of each bit in the client hello packet. The number at the top present each bit, numbered from 0 to 31, and the label represents the field and their position in the packet. You'll commonly find diagrams like this in the IETF's RFC documents, which describe protocols. 0, 1, 2, 3, type, TLS, packet, length, message, random. The structure of a TLS handshake packet. All packets in the TLS 1.2 protocol begin with a type field. This field identifies the type of packet being sent. All messages associated with the TLS handshake are assigned the type 0 times 16, indicating they are part of a handshake record. The next 16 bits represent the TLS version, and the value of 0x0303 represents version 1.2. The 16 bits after that represent the packet length, which is the total length of the packet in bytes. Next is the 8-bit message type. Packet length, message type, message. Next is the 8-bit random. Okay, for the list of type of messages exchanged during the TLS handshake, the value represents a client hello message. Following that is a 24-bit indicating message length. That is the number of bytes remaining in the packet. Then comes the 16-bit client TLS version, which is the version of the TLS that is currently running, and the 32-bit client random, a not supplied during the TLS exchange. The next 8 bits represents the session ID length. Session ID identifies a session and is used to resume incomplete or failed messages. We won't use this field, and as you'll see, we'll set it to length 0. The cipher suite length is the length in bytes of the next field, which contains the cipher suites. In this case, we will set the value of this field to indicate that the supported cipher suite information is 2 bytes long. As for the types of ciphers the client supports, will use the value indicating that the client supports RSA keys. So, cipher suites. Exchanges and uses the 128-bit AES and cipher block chaining mode for encryption. See Chapter 5 for more information on block cipher modes. The final 16 bits represents an extension length. We're not using any extensions, so we'll set the value to 0. We can manually construct the packet by setting each of the bytes, set 8 bytes ourselves. We'll represent the value as hexadecimal numbers. Copy the following code, snip it into your heartbleed.py file. I've pointed out each hexadecimal value using comments. So we already have this written in here, I'm sure of it. Great, we've constructed the client hello message, but before we send it, let's discuss the structure of the packets we'll receive in response. Reading the server response. So what I'm going to do is, I want to do a 30-minute video. I'm going to break this up in different videos. just to, so I don't want to make a really long video this time. Um, Reading the server response. The server will transmit 4 packets, all of which have a similar structure to the client hello message. Type, version, packet length, and message type field appears in the same location. We can detect the server done message by inspecting the message type, located in the 6 byte. A hexadecimal value of whatever represents the server hello, whereas values of that and that represent the server certificate message, server key exchange message, and server done message, respectively. We're not interested in actually establishing an encrypted connection, so we can ignore all the messages we receive from the server until we get the server done message. Once we've received this message, we'll know that the server has completed its part of the handshake, and we can now send the first heartbeat message. Create a constant to hold the hexadecimal value representing the type server done. Now let's write a helper function that will ensure we correctly receive all the bytes associated with the TLS packet. This function will let us receive a fixed number of bytes from the socket. The function will wait for the operating system to be finished loading bytes into the socket buffer, and then we'll continue reading from the buffer until we read the specified number of bytes. We use the select function to monitor the socket. After the operating system has written to the buffer, the select function will unblock and allow the program to process the next line. The select function takes 3 parameters, which represents a list of communication channels to monitor. The first list contains channels that are readable. The second contains channels that are writable, and the third channel that should be monitored for errors. When a socket becomes readable or writable or contain errors, it is returned by the select function. Then the socket attempts to read the remaining bytes from the socket buffer. The parameter represents the maximum number of bytes to read. If this is less than the maximum number of bytes available, the socket receive function will read as many bytes as available. The next function will read packets from the socket and extract their type, version, and payload. We read 6 bytes from the socket. The 6 bytes represent the header field associated with the TLS packet discussed earlier, type, version, length, and message type. Then we'll use the struct library to unpack the bytes into variables. The greater than sign tells the struct library to interpret the bits as a big-ended format. In this big-ended format, the most significant byte is the smallest address. Network packets are normally in big endian formats. The B tells the struct library to extract the first byte as an unsigned char, a value between 0 and 255. And the H tells the struct library to extract the next 2 bytes as unsigned short. We place the first 8 byte values into the variable and the next 2 bytes into the version variable. Then we place the following 2 bytes in the length variable and the final byte in the message type variable. The length field represents the length of the payload. If it's greater than 0, we can read the remaining bytes associated with the packet from the socket. All messages have a similar structure, so we can reuse the same read packet method for all subsequent packets we receive. Alright, let me see. Crafting the malicious heartbeat request. Once we receive the server done message, we can send the heartbeat request. Figure 9.4 represents the layout of the heartbeat packet. Both the request and response packets follow this structure. The 6-byte identifies whether the packet is either a response or a request. Malicious heartbeat packet. Type, version, response, request, payload. Our mailform request looks like this. Heartbeat. Notice the discrepancy between the packet length and the 3 bytes will represent the remaining bytes of the packet in the payload length of 64 kilobytes. There you go, yeah. Shouldn't the packet length include the payload length? How is this possible that the payload length is larger than the total packet size? This is the mailform aspect of the request. Remember from Figure 9.1 that we're specifying a payload length of 64 kilobytes, which is the largest we can specify with the allotted 16 bits. But that's the actual payload size. Is 0. Reading the leaked memory contents. As mentioned earlier, heartbeat packets are limited to maximum length of 16 kilobytes. This means that the 64 kilobytes of memory the server sends in response will be split across 4 16 kilobyte packets. Let's write the function that we read all 4 packets from the socket and combine their payloads into a single 64 kilobyte payload. We call the read packet function 4 times to read the 4 heartbeat responses we expect from the vulnerable server. Then we combine all payloads of the 4 responses to a single payload. Write an exploit function. The following code snippets implement the exploit function, which will send the mailform heartbeat requests and read the 4 heartbeat response packets. The type value of 0x15 indicates a heartbeat response packet. Next, this is one heartbeat response. Next, we'll send the mailform request, and then we'll read 4 response packets. Lastly, we'll print the payload. Print no heartbeat received. Putting it together. In the program's main method, we'll create the socket and send the packets and wait for the server done response. Copy the following code into your file. Already did that. After we've created the socket, we can connect to the IP address. Let me see if we've got that down. Well, anyways, after creating it, we connect to the IP address that was passed as a command line. We'll connect to port 443 because it's associated with TLS protocol we're attacking. Once connected, we initiated TLS version 1.2 connection by sending the client hello message. Then we'll listen to the response messages and inspect each type until we receive the server done message. Lastly, we call the exploit function. So we're going to stop right there and then we're going to do this fuzzing. So this one will probably be building the let's look at the building the what was it? .py? The .py file? The heartbleed.py. So let's look at that. So we've got our import libraries. We've got the first initial request to to talk, I guess, to the client. Handshake, TLS version. Here's all the information. Session ID, this is where we're setting everything, I guess. Server hello done. It receives it sends back done request. Read packet. And this is the heartbeat exploit. Read heartbeat, here's the exploit. And the def mean, I guess, is the socket connects and does it read it? No, that's right here. Is read it. Prints no heartbeat received. Anyways, so yeah, here's our code. Alright, that was HackTheFile, and on the next video we're gonna do some fuzzing. I guess we're gonna try to create a fuzzing program. So I tried to run this one, but I don't think that it's complete yet. It doesn't say run it. It just says start making it, and then I guess it's probably gonna run it at the end. So I guess we'll see. So I'm not gonna run it yet. Besides, it's not even working. I actually did try to run it, and it's not working. So, all right. I hope you learned a little bit, and see you next time.